OK， 好，我们在礼拜三的时候讲到了这一个matrix representation of a linear combination。好，那 matrix representation of a linear combination 其实是这整个线性代数当中一个非常非常关键的基础。好，那因为最主要是因为说在这些线性转换的过程当中，有时候我们在实际操作上面会非常麻烦。如果我可以把这个线性转换这个线性转换把它改成一个矩阵的表示法的时候，那我们知道电脑很好做矩阵，不管你几个回圈的你几个回圈，反正你就用回圈去做矩阵。好，那所以电脑很容易做矩阵的时候，如果我可以把一个很复杂的线性转换，把它转换成为一个矩阵的形式的话，那我们就很容易的就让电脑去执行这些计算。好，因为人脑在做计算的时候时常会算错，电脑不太会算错。做回圈，我们是 i 等于1到 n，j 等于1到 m， 然后一直让它做回圈，电脑做得非常精准。但是我们人做的话，就会时常出错误。好，所以如果说我们可以把一个线性转换把它变成矩阵的形式的话，那甚至这个部分，我们有越来越多的维度的时候，我们维度非常大。好，那这个矩阵也可能变得非常大，甚至我们可以从这个矩阵变成张量，变成 tensor。好，那各位如果说各位以后如果对人工智慧有兴趣的话，在很多的 DNN 好deep neural network 好这样子的深度学习的情况之下，你要执行的是一种叫做 TensorFlow。也就张量的流程，张量分析。那这个时候呢，其实我们把这些所有的流程变成一个类似矩阵的方式，一直去做运算。好，所以在这个地方在这一章的我们讲说 application 的部分，就线性代数，我们可以看到很多的理论证明，有一大堆理论证明。那实际上真正在应用层面的时候，好，在 application 的部分的话，就是把它变成矩阵。所以实际上线性代数，我们从另外一方面来讲的话，实际上我们在做的是什么？在做矩阵运算。我们要怎么样去把矩阵给找到，然后在之后一连串的这个matrix operation。好，那所以我们在前2章的部分就是在打这个基底。好，所以前2章很痛苦，就是说这里面有很多的理论基础，然后非常的抽象。好，但是一旦变成矩阵的时候，大家就很会做了。好，你到第3章的时候，你们去看到第3章的讲义的时候，那个就你们就会变突然之间豁然开朗，好熟悉。好，所以这2章会是比较辛苦的部分。好，那先在这边跟各位讲一下 ，OK？ 好 ，So on Wednesday, we discussed about the matrix representation of a linear transformation. And for a linear transformation, we can convert it into a matrix. So the operation of linear transformation can be considered as a matrix operation. And so for most of you, you may be very familiar with the matrix operation because you have already learned it in your high school mathematics. So right now, we want to expand this matrix operation or linear transformation from 2 domains to more domains. 好 to 2 vector space to more vector space. So the next one we're going to discuss is composition of linear transformation and the matrix representation. Okay, so what is the composition of linear transformation? So right now, actually, we have vector space. We have more than 2 vector space. So for example, I have the first vector space V, and then we have a next vector space W. And furthermore, we have another vector space. I call it Z. So from V to W, we define a linear transformation as T. So T will be transformed vectors from V to W. So if I have a vector X here, then I have T T sub x in W. Okay? And then we define another vector, another linear transformation from W to Z. We define it as U. So U convert or transformed the vectors from W to Z. So then we further transform this vector if we assume it's Y in W. Then we transform Y vector from W vector space to Z vector space. So we write it as U sub Y. But because we know that Y is equal to T sub X, so we can write it as U times U sub T sub X. And then we can use this notation to describe this, this transformation. So now we see that we can define a new linear transformation directly from V to Z. So we define this transformation as UT, which is a new linear transformation from V directly to Z. Okay, so this kind of linear transformation, we combine the two linear transformations together. So we call it as the composition of linear transformation. Okay, so right now we have to be careful. If I have a basis here, for example, if I have a basis, we call it as alpha, and then it contains V1 to Vn. We have another basis here, beta. It contains W1 to Wm. And I also have another basis, we call it as gamma, which is consists of Z1 to Zp. So here, dimension V equals n. Here, dimension W equals m. And here, dimension Z equals p. So now we can, because from the previous session, we know that we can always convert a linear transformation into a matrix. So we can convert the linear transformation of T from V to W with respect to alpha and the beta. Then we know this one is a M by N matrix. Okay, and then we can find that U is from beta to gamma, from basis beta to basis gamma, and then this one is an P by M matrix. Okay, so the composition of a linear transformation UT, which will transform the vectors from V to W, V to Z directly. So the source basis is alpha. The destination basis is gamma. Then we have, because I have a P vectors, P distinct linearly independent vectors here, and the N distinct linearly independent vector here. So the new matrix, the composition, the matrix that represents this composition of linear transformation becomes a P by N matrix. Becomes a P by N matrix. Okay, that is because I have T, this M by N. So for the composition here, I have P by M, and here I have M by N. So combine them together, I have P by N matrix. Follow the matrix operation we have already known in your high school mathematics. So I have a P by N matrix here. Okay, so now it's very clear that, okay, if I can transform the vector from V to Z, I can use this. I can use this this linear transformation, the composition of this linear transformation. If I want to transform the vector from Z to Z back to V, then I should go this way. I should go this way. So if I have another linear transformation, for example, or I will call it as U1, and this is U2. So if I want to transform it back from Z back to V, then what I should do? I should transform the vector from Z first back to W. So this is U1 Z. And then transform the U1 Z back to V by U2. So then we transform it back to U2 from here, it's in W, and back to V. So I have U2, U1, Z. Okay, we have to know that this kind of transformation, this kind of composition or linear transformation is not commutative. So we will say that TU may not be equal to UT. TU may not be equal to UT. And even TU, because right now we have UT, we have the definition of UT, definition of the composition or linear transformation from V to Z. But do we have UT, do we have TU? Do we have TU linear transformation? It may not exist. It may not exist. Why is that? Because if the linear composition, if the composition of linear transformation is expressed by TU, which means that here let me erase it. I transform, maybe TU. Okay, so here I have to say that, okay, so because U, we say U is from W to Z, but T is from V to W. So if I have TU, which means that I first transform vector from W to Z, but T is operated from V to W. So T may be independent of Z. T may have no any relationship with Z because T is from V to W. It's not transforming any vectors from Z to any other vector space. So T here, so we transform T U, for example, UW. Okay, so we transform UW is in Z, but Z does not belong to V. So this kind of transformation is meaningless. This kind of transformation is meaningless because T transforms only vectors in V to W. So it will not transform any vector from Z to any other vector space. So TU may not exist. So it's not commutative. So we have to know that. Okay, and by using the matrix representation, we can see that. Okay, because U is an P by U is an P by M matrix, and the T is an M by N matrix. How can I operate a multiplication of matrix with a M by N and a P by M? We can operate it. We can have P by M, M by N. So the resulting matrix becomes P by N. But if I have M by N and P by M, it doesn't match to each other. The number of elements are not the same. So we cannot, there's no such kind of matrix operation. So UT cannot be commutative. This is very important. Okay, so here right now we are going to, with this background, with this composition of linear transformation background, then we will begin to discuss Theorem 2.9. Theorem 2.9 says that, okay, if I have a composition of linear transformation and in which U and T are linear, so that the composition of linear transformation is also linear. So here, let VW and Z be vector spaces over the same field, and let T is from V to W and U is from W to Z. They both are linear. Then the composition of linear transformation UT, that is transforming vector from V to Z, that is also linear. So we want to prove that. So whatever proof that want to prove the operation is the transformation is linear, we have to do that. Okay, so for if I want to prove T is linear, so then what do we need to do? We need to say T sub C sub x plus y, T sub Cs plus y equals CTx plus y. If this statement is true, then T is linear. Okay, so what we need to prove is that, okay, I have UT. Okay, and we operate it on here because in the lecture note is AX plus Y, so I say AX plus Y. So our goal is to prove that if I transform this AX plus Y vectors from V to Z directly, then we wish that this one will be equal to A times UT sub X plus UT sub Y. We want to prove this. So if the statement is correct, then UT is linear. Okay, so then we just follow the standard operation of a linear transformation. So because T and U are both linear, so if we have UT AX plus Y, then we need to operate T sub AX plus Y first. And because we know T is linear, so we can easily get U sub A times T sub X plus T sub Y. T sub Y. Okay, because T is linear. Then because U is linear, so I have U of T sub X plus U sub T sub Y. And because U is linear, so I can take the scalar multiplication of a vector. We can take this scalar out of this transformation. So I have A times U T sub X plus U T sub Y. So then we can put them together. I have A times T sub U X plus T U sub Y. So I get this result. So I prove that this transformation is linear. Okay? And then the next theorem, 2.10, here we assume we only operate the vectors from V to V. From V to V. Okay, so in between V, these two V vector space, there are a lot of linear transformation. For example, it has T, it has U1, it has U2. So in fact, this linear transformation form a vector space from V to V, and we can just, in brief, we can just briefly express it. Okay, so here, this linear transformation forms a vector space. And this vector space, we denote it as linear transformation from V to V. Okay, so we have a bunch of linear transformation here. And we can also know that for this linear transformation, T beta, it is an n by n matrix. For all the linear transformation here, the matrix representation are all squares, square matrix, because it's from V to V. Okay, they are all n by n matrix. They are all n by n matrix. Okay, so now what we are going to do is to prove that, okay, I have a linear combination of the linear transformation. We call it as U1 plus U2. And then we further transform. So from here, I can have an X here, and transform it to the same vector space. We have U1 plus U2 X. And then we further transform it to V, and then we by using the T transformation. So then I can have T sub U1 plus U2 of X. So now we want to prove that this transformation will be equal to T sub U1 X plus T sub U2 X, which means that T operate on U1 plus U2 equals TU1 plus TU2. Okay, so it will follow the distribution law here. And actually, it's pretty simple. You just use the same procedure. We put X here, and then we can have U1 plus U2X will be equal to U1X plus U2X. And then we operate it from by using T transformation. So then I can have this result. And the same as here. Okay. So actually, the following 4 statements are simple, and the proof is quite straightforward. So I'm not going to prove it detailedly. So I will just let them for you as your homework, okay, or as your exercise. Okay, but right now, what we have to be cautious is that, Okay, from the textbook, it says a more general result holds for linear transformation that have domains unequal to their codomains. So what does domain and codomains mean? Actually, it's just the source vector space. We call the source vector space as the domain. And after transformation, we call this destination vector space as codomain. Okay, so which is roughly the same idea. But right now, when we use this statement, we have to be very, very cautious because some of them may not be true. In general case, we have to put a lot of restriction on this a lot of restriction to get this false statement correct. For example, for C, okay, for C, if V and W are not with the same dimension, then for C we have to rewrite it, and we have to be very, very carefully rewrite it. Okay, so for C, in C we say that Ti equals It equals T. Okay, this looks very simple, but if you want to apply this linear transform, apply it to a general case, then this one has to be rewritten. So right now I have V to W. So I have a linear transformation as T. Okay, so actually we have an identity transformation from V to V. We write it as IV. We also have an identity transformation from W to W. We call it as IW. So if dimension V equals N, dimension W equals M, then we have to be very careful because dimension V is not equal to dimension W. So T, the matrix representation of T is no longer a square matrix. It's an M by N matrix. It's not square anymore. Okay, so here IV is with respect to, if I have the basis beta here, the basis gamma here. If I have an identity transformation of V, then with respect to beta, this matrix is an N by N matrix. And the IW with respect to gamma is an M by M matrix. Okay, so if I want to have this statement correct, what I'm going to do is that, okay, we have to be very careful that for these two linear transformation, which one will be operated first? The later one. This one will be operated first. So in this scenario, then I should do the identity transformation first. From V to V, I have an identity transformation IV. Then I can transform it to W. Okay, so the composition of linear transformation becomes TIV. Okay, and if I put this one here, IT, what am I doing? First of all, we have to operate T first. So if we operate T first, we first convert or transform vector from V to W. We have T here. But then I means the identity transformation in W. So the composition of linear transformation becomes IWT. So if these two are identical, I have T IV equals IWT. Okay, let's check its dimension. So this should be an n by n matrix. This should be an m by n matrix. So I have m by n times n by n. So the resulting transformation, the resulting matrix should be m by n. Okay, for this one, I have T m by n, but for IW, it's m by m. So IWT becomes m by n. So now we can know that for these two composition or linear transformation, they are with the same dimension, m by n. And also, it will be equals to T. Because T is also an m by n matrix. Okay, so now we have to rewrite it as this form. We have to rewrite it as this form. So here, even though it says that the textbook claims that a more general result holds for linear transformations that have domains unequal to their codomains, but we have to modify these four statements carefully, very, very carefully, because for this transformation U1, U2, they may not from the same vector space to the same vector space, because, for example, here, if I'll plot it here. If U1, U2 is from V to W, and this one has dimension n, this one has dimension m, do we have U1, U2 composition or linear transformation? The answer is no. Because U1 only convert vector from V to W. U2 only convert vector from V to W. So if I do it this way, I have U1, U2x. This U2x is in W, not in V. But U1 only transform vector from V to W. So U1 will not have any effective operation on vectors in W. So we cannot do it. So this kind of transformation doesn't exist. Okay, so here, even though this statement can be true, but we have to put a lot of restrictions to get this fourth statement true, or we have to modify the statement here. Okay, but I'm not going to go to the detailed. Okay, now the next one is very important. The next one is very important. So it defines how you calculate the multiplication of matrix. Okay, so here, we have, so let's plot the diagram first. Okay, I have V to W to Z. And here I have alpha, that is the spaces of V with n vectors. I have beta W1 to Wm, n vectors for W. And I have gamma from Z1 to Zp. That is the basis for Z. Then I have the linear transformation T from V to W. I have linear transformation U from W to Z. And the composition of linear transformation from V to Z directly, that is UT. Okay, So because we have already know we have the linear transformation from V to W. So we know that we assume A is the matrix representation of U, which is from beta to Z, beta to gamma. And I have another matrix B that represents the linear transformation of T from alpha to beta. So by definition, okay, I can say T sub Vj will be equal to summation I equals 1 to M. And T is represented by B, so I have Bij times Wi. We have this kind of statement here. Let me see. Okay. Okay, here. So we have this. We can construct the matrix by using this approach. Okay, and then we have use of W because U is converting vectors from W to Z. So I have use of W. Let me check. WK. I'm using WK. Okay, WK, and let me see. Maybe I have to change the variable a little bit. Sorry. I have to be consistent with the lecture note here. Let me rewrite it. Sorry. T sub Vj, I can write as summation K equals 1 to M. And Bkj times Wk. Okay, to make it more clear. And then U, because U transform vector from W to Z. So I transform the vectors in the basis. And then it will be equal to summation I equals 1 to P A I K AIKZI. So I will rewrite it in this form. Okay, actually we can find it in page we can find it in page 18. Just change some variables here. Okay, so we get this. Now we want to find the matrix representation of UT. So here we can convert. What I'm going to do is that I can, because UT is converting vector from V to W directly. So I'm going to write UT by using Vj. So so one of the vectors in the basis, and it will become summation I equals 1 to P Cij times Zi. We want to find this. And how can we find it? Of course, we can do it step by step. UT Vj, which will be equals to U operates on T sub Vj. And the T sub Vj is here. So I have U times T sub Vj. T sub Vj becomes summation K equals 1 to M Bkj times Wk. Okay, and because U is a linear combination, U is a linear transformation, so I can write as summation K equals 1 to M Bkj times U Wk. And then we also have Wk here. Okay, T sub Vj is here. So I replace use of WK by this expression. So I have summation K equals 1 to M BKJ times summation I equals 1 to P AIK times ZI. What we are going to find is what is Cij. We want to find what is Cij. So then we move this summation term out of this term. So I have summation I equals 1 to P. Then I have A, I, K. Because this is a vector, and here, Zi is a vector. But these are all scalars. So for all these terms are not vectors, they are scalars. So Zi is the only individual vectors in this expression. So then I have summation K equals 1 to M BKJ. And then I use a bracket to cover it and have Zi here. So right now, what we are going to do is that we move this one out. So then I can write it as summation I equals 1 to P and the summation K equals 1 to M AIK times BKJ times ZI. So compare this form with this form. We can find the coefficients here. Cij equals summation K equals 1 to M AIK times BKJ. Okay, so we get this result. What does this mean? What does this mean? Okay, after the linear transformation, after the composition of linear transformation, we can express, because we express U from beta to gamma as A matrix, T from alpha to beta as B matrix. And also right now I have U sub T that is from alpha to gamma, that is C matrix. So C will have C11, C21 to CP1, and C1n, C2n to CPn. This is an P by N matrix. So for one of the element here, Cij, it will be equal to here. A will becomes a P by, this is an P by M matrix. This is an M by N matrix. So I have A11, A12 to A1n, A21, A22 to A2n, etc. This A1M, A2M, AP1, AP2 to APM. Okay, and I have B1, B21 to BM1, and the B12, B22 to BM2, etc. to B1n, B2n to BMN. I have this matrix multiplication. So Cij means that I have, from the result I have Cij equals summation k equals 1 to m, and aik times bkj. So that means I have the ith row here. This is the ith row. So the ith row contains ai1, ai2, ai3 to aim. And the jth column here. So ith row has ai1, ai2 to aim. And the jth column has b1j, b2j to bmj. So this is an m-tuple row vector. This is an m-tuple column vectors. So what we are doing is that we multiply with ai1 to a1j plus ai2 to multiplied by b2j and ai3 times b3j, etc. to aim times bmj. So right now, what we are doing is here. What we are doing here is we are going to calculate the multiplication of two matrices. So this is how we operate the matrix multiplication. How we operate the matrix multiplication. Okay, so by using this way, we can calculate so here we define that, okay, let A be an m by n matrix and the B be an n by p matrix. We define the product of A and the B, and we denote it as AB to be an m by p matrix, such that Cij will become ABIJ, and the elements Cij, the ith row and the jth column, the intersection of ith row and jth column, that is the Cij, and which will be equals to k equals 1 to n aik to bkj. Okay, so we say that the product of A and B and the AB is defined. AB is defined. Okay. So by using this way, we can find the product of two matrices. Okay. Here I have a little bit different. Definition here, because here I use A as P by M and B as M by N here. But in the lecture notes, A is M by N and the B is N by P. Okay, so it's a little bit different here. But anyway, the result should be valid. Okay, so we define the matrix operation, matrix multiplication of two matrices. So this is what you have already learned in your high school mathematics. You have already learned how to multiply two matrices. But at the time, the teacher only told you that, okay, you do it this way. You do it this way. He or she may not give you how it forms, how it translates from the theory to operation. So here we give you the theoretical background to the multiplication of matrix. Okay, so the next one is the product of two matrices is not commutative. We just mentioned that it's not commutative because AB is not necessarily to be equal to BA, even with the same dimension. Either A is an n by n matrix, B is an n by n matrix. they are not the same. They are not the same. Because if we have A is n by n, if I have A is n by n, A11, A21 to AN1, A1n, A2n to ANn, and the times B11, B21 to BN1, and the B1n to BNN. So the Cij will becomes AI summation k equals 1 to an AIK times BKJ. But if we commute, if we change the order, change the order of the two matrices, then if I have B times A, okay, so this one, so I can here I will have A1K, AI1 times B1J, plus AI2 times B2J, etc. to AIN times BNJ. But if I change the order, if we multiply it with B times A, then I will have BI1 times A1J plus BI2 times B2J, plus etc. BIN times ANJ. Okay, the elements are not the same. The A1 AIJ is not equal to AJ, is not equal to BIJ. So these two, even with the same dimension, n by n, n by n, n by n, n by n, the resulting multiplication of matrices are not the same. Because this is the combination AIK times BKI, and then this one from B times A, I have BI1, BIK times AKJ. So these terms are not identical either. These are not identical either. So we cannot simply commute the two matrices. Okay, so the product of two matrices is not commutative. So this is very important. Okay, let's take a break for 10 minutes.
他这个手这一句话是入 B 所然后就可以扣分数。
Okay, so let's start the class right now. 那个拿作业待会儿再下课再来拿吧。Okay, so the next fact we want to discuss is that if A is an n by n matrix and B is an n by p matrix, so we have the product of A and B is defined. So the product of A and B becomes an n by p matrix, and then we want to transpose the matrix. So then the transpose matrix of A times B becomes a p by n matrix, and then we want to show that after transpose, then ABT equals BT times AT. Okay, so we want to calculate it. And actually, we just follow the definition of the product of a matrix. So here we first calculate AB, and then we transpose it. Okay, so here after we transpose the product of AB. And so we take the element, the ith row and the jth column. So it will be the ABJT, ABJI, because here, if we let C equals this one, C11 to C1n, and here, let me see, it's an n by p matrix. So M1 to CMP. Okay, so I have a P column, and here I have M rows. Okay, so if I transpose it, it will becomes the C11, C21 to CM1, and the C12 to C1P to CMP. Okay, and CM2. Okay, so I have this transpose matrix. So here, the transpose matrix Ij will be equals to Cji. Just follow this fact. Then we know that C is equal to A times B. So we just follow this concept. So after transpose of matrix C, its ijth element will be the original matrix C's jith element. And by taking the definition of the jith element like this, I can have it as a summation from k equals 1 to n ajk times bki. Okay, and then this is for the left hand side. And for the right hand side, we want to know the bt times at, the ijth element. What will it be? So bt times at is ij element. Then I can calculate it as, so first of all, I will have summation k equals 1 to n bt's ik's element times at's kj's element. And then because we are doing transpose, so then bt ik will become bki. bt ik will become bki. And the at kj becomes ajk. So I have bki times ajk, and then we reverse the order. We have ajk times bki. So from k equals 1 to n, so then I have a, b, ji's element. A times b, and we take the ji's element, and which will be equal to this one. Okay, which will be equal to this one. So we just do the transpose. So here we have to be very careful. So when we do the transpose, the order should be reversed. So at the very beginning it's A, B, then the order after transpose, it becomes B's transpose times A's transpose. Okay, so that is the what we are going to discuss here. And then we want to discuss theorem 2.11. 2.11 says that let VWZ be finite dimensional vector spaces with ordered bases alpha, beta, and gamma, respectively. And let T be the vector linear transformation from V to W, and the U is from W to Z, and they are both linear transformations. And then the matrix representation of this composition of linear transformation from alpha to gamma, that is from V to Z, will be equals to the matrix multiplication of U and T. And in fact, we have already done it here in the previous page. We have already done it in this page. Okay, so we are not going to prove it too. We are not going to prove it either. So because this is pretty straightforward. And also, if V is finite dimensional vector space with an ordered basis beta, and that TU is a linear transformation between the same vector space, then UT with respect to beta will be equals to U with respect to beta, and the matrix representation of T with respect to beta. So this is also very straightforward. Okay, so we are not going to prove it either. So because it has already been discussed here. Because here this is a more general case, and this is a special case. Okay, so now we will take some examples. Okay, so if I have a U linear transformation of U, it transforms a degree 3 polynomial to a degree 2 polynomial by taking the derivative of the polynomial. And the T is the linear transformation from degree 2 polynomial to degree 3 polynomial by taking the integral of the degree 2 polynomial. Then we have use of fx. Fx here is a degree 3 polynomial. So we have, if we take this linear transformation by taking the derivative of this polynomial, and the T is defined by the integral of the polynomial. So then we can easily find that. So right now, how can I find U from beta to gamma? How can I find it? The way is that we take the vectors from its basis, and then I have summation I equals 1 to n, and Aij times Wi. So I will take this one, and the Aij will becomes the element in the matrix representation of U. So what I'm going to do is that, okay, right now we know U is from degree 2 polynomial to degree 3 polynomial. So the basis, the standard order basis, beta should be 1x squared. Gamma should be 1x squared. And from degree 3 to degree 2. Okay, so sorry, here. From degree 3 to degree 2. Okay, and then, so here I have another vector, x3. So we take use of fx, and then we let fx be equal to 1x squared, x to the cubic, 1 by 1. So if fx equals 1, then use of 1 equals 0, which means 0 plus 0x plus 0x squared. So then the first column of U from beta to gamma becomes 0, 0, 0. The first column, 0, 0, 0. And then take x. So if I operate x, I can have it equals 1. Then it will be 1 times 1 plus 0 times x plus 0 times x squared. So the second column becomes 1, 0, 0. And then we take u sub x squared. Then I get 2x. It will be equal to 0 times 1 plus 2 times x plus 0 times x squared. So I have 0, 2, 0. And the third one, u operates on x cubic. Then I have 3x squared equals 0 times 1 plus 0 times x plus 3 times x squared. I have 0, 0, 3. So I can find the matrix here. The matrix representation of U. And then what I'm going to do is to find the matrix representation of T. So it takes the integral of a degree 2 polynomial. So now T, we will transform it from P2 to P3. So this is T. And the beta here, I may take the, let me take the, from gamma to, here from gamma to beta. Okay, here is 1x x squared. And the beta is 1x x squared, x to the power of 3. Then we take the integral. So we take t sub 1. We get, okay, 0 times 1 plus 1 times x plus 0 times x squared plus 0 times x to the cubic. And the second vector here, t sub x. So I have 0 times 1 plus 0 times x plus 1/2 times x squared plus 0 times x to the cubic. And here I have t sub x squared. Then I have 0, 1 plus 0 times x plus 0 times x squared plus 1/3 x to the cubic. So now I have a 4×3 matrix. 0, 1, 0, 0, 0, 0, 1/2, 0, 0, 0, 0, 1/3. So this is the matrix representation of T from gamma to beta. Okay, then we can easily find that if I have the linear transformation, if I have a linear transformation from P2, first of all, from P2F to P3F. This is T. And then from P3 back to P2. This is U. So I can have UT. I can have UT here. So the matrix representation of UT, because here this is gamma, this is beta, this is gamma. It's from gamma to gamma. Okay, it's from gamma to gamma. Then I have U from beta to gamma and the T from gamma to beta. And then we take the matrix product of these two matrices. And then we can get the identity matrix here. I can get the identity matrix here. So here, degree, here is a degree 2 polynomial has dimension 3. This has dimension 4. This has dimension 3. So right now I have 3×3 matrix. Because for this one it's 3×4 matrix times a 4×3 matrix. So I can have the 3×3 matrix. And the resulting matrix become 1, 0, 0, 0, 1, 0, and 0, 0, 1. We call this matrix as identity matrix. We call this matrix as identity matrix. Okay, so here and then we will define the identity matrix is delta 1 1, delta 2 1, delta 3 1 for the 3 by 3 matrix. Then I have delta 1 1, delta 2 1, delta 3 1, delta 1 2, delta 2 2, delta 3 2, delta 1 3, delta 2 3, delta 3 3, and in which we call this delta as Kronecker delta. We call this delta as Kronecker delta, and it's defined by delta ij equals 1 if I equals j, and the delta ij equals 0 if I is not equal to j. So then we define this Kronecker delta, and then the matrix, the identity matrix, is consisted of the Kronecker delta. Okay, n by n Kronecker delta. So we have this identity matrix. Okay, this is pretty simple. And then for this for the composition for the theorem 2.12, the theorem 2.12 is that let A be an n by n matrix and B and C are n by p matrix and D and E are q by n matrix. Then A times B plus C, the distribution law is valid. So that A times B plus C, because B and C have the same dimension. So if AB is defined, AC is also defined. Okay, then I have AB plus AC, and if D plus E times A, I have DA plus EA, and etc. Actually, this is just the same. This theory is just the same as what we have discussed here, 2.10. It's the same. If you take the matrix representation of T as A matrix, U1, U2 as B and C matrix, and you can find they are all identical. So here, just as I mentioned, because in theorem 2.10 we only discuss the vector space, only one vector space, but it has more general result for different dimensions. So here, this theorem is identical to theorem 2.10, except for that here we only consider the matrix. But in theorem 2.10, we have linear transformation. But actually, if we take the matrix representation of the linear transformation, these two theorems are identical. So I'm not going to discuss this theorem anymore, because you can easily find it by taking the by taking the proof of theorem 2.10. So we will just skip 2.12, and the corollary, same. Corollary say that okay, then we can have this product of matrix is a linear transformation. We can get its linear combination. So if I have a linear combination of BI's, and then I can take A times BI independently, and then sum them together. So the same as this one. So the corollary is because if this hold, A hold, then B hold. Okay, so you just follow the standard operations of the matrix multiplications, then you can get the whole result here. So I'm not going to redo it one by one. And then for theorem 2.13, it says that A is an n by n matrix and B is an n by p matrix. And for each j is from 1 to p. And let uj and vj denotes the j's columns of A, B, and B respectively. Then uj equals A times vj, vj equals B times ej, where ej is the j standard vectors of fp. Okay. So what are we going to prove here? So let's just just read this theorem carefully. So A is an n by n matrix. A is an n by n matrix, so A, I can write it as A equals A11, A21 to AM1, A12, A22 to AM2, and A1n, A2n to AMN. And B equals B11, B21 to Bn1, B12, B22 to Bn2, etc. B1p, B2p to Bnp. Okay, right now we defined the jth column of B as Vj. Okay, the jth column here, Vj denotes the jth column of B, and then after we take the multiplication of A and B, then we have AB 11 and AB 21 to AB M1, etc. to AB 1P, AB 2P to AB MP. And then the jth column becomes Uj. The jth column becomes Uj. So first of all, so we want to prove that the Uj will be equal to A times Vj, and the Vj will be equal to B times Ej. Okay, so let's prove B first, because B is much easier. So if we take, because we know the jth column Vj equals B1j, B2j to Bnj, and then we just take B times Ej. So B times Ej, what is Ej? Ej is the jth element in this column vector, and the jth element in this column vector equals 1, and for the rest of them are 0. So if we take Ej, this Ej as this form, then we just perform the multiplication with times 0, 0, 1, 0. So then we can find, okay, B11 times 0 equals 0, B12 times 0, and until B1j. So we can get that. Okay, so we can get that. We will, after we do the multiplication, then we will get the first element B1j. And the second row, B21 to B22, B21 times 0, B22 times 0, and the B2j times 1. So I have B2j. Just follow the multiplication procedure, and I can have Bnj. So we can easily get this one equals Vj. So this one is quite straightforward for B. And for A, actually, it's also, we also follow the same procedure. So Uj will be the jth column of A times B. So it will be AB 1j, AB 2j to AB mj. So just follow the procedure, and then so I can have AB1j, AB2j to ABMj. And then for AB1j, it will be summation k equals 1 to n A1k times bkj. And AB2j, there will be A2k times B2 pkj, etc. And then when we calculate it, we can find it will becomes A matrix times B1J, B2J, Bnj, and that will becomes A times Vj. So theorem 2.13 is also easy. Okay, now we're going to prove theorem 2.14. Theorem 2.14. And for the theorem 2.14, we let V and W be finite dimensional vector spaces, having ordered basis beta and alpha, beta and gamma, respectively, and let T is from V to W. That is linear. And then we want to calculate that T of U with respect to gamma will be equals to T matrix from beta to gamma times U with respect to beta. So what does it mean? Okay, this one is compared with the previous theorem. This one is more important. This one is more important. Is more important than the previous several theorems. Okay, so what does it say? Okay, I have a vector space here V, and I have a vector space here W. So here I have beta. That is the basis of V. So I have order basis with V1, V2 to Vn. And I have a vector set gamma, which is a basis. So I have W1, W2 to Wm. And I also have a linear transformation T. So we want to transform X to W by taking this linear transformation. Okay, so here, what we are going to prove is that we want to prove that T sub X. Sorry, here okay. The lecture notes use U. Sorry, so I will use U2. U and the T sub U. Okay, now what we are going to prove is that T sub U with respect to gamma, because after transformation, T sub U is in W. So in W, the basis is gamma. So I have to take this vector with respect to the basis gamma. Okay, we want to prove that it will become T from beta to gamma. This is a matrix representation of linear transformation. T and U is a vector, the coordinate vector with respect to beta. Okay, so we want to prove it. So now what I'm going to do is that, okay, in the textbook, it provides this proof, but it's very difficult to be understood. So I'm not going to take this one. I'm just going to do it with the most generic approach. Okay, so here we can see that in the left-hand side for this one, okay, we know that because when we take the linear transformation on the basis vectors, we have T sub Vj equals summation I equals 1 to M Aij times Wi. We know it already. We have known it already. So we can write T from beta to gamma as the element composed of these coefficients. Okay, so we have known this already. Now we let, because U belongs to vector space V, so U can be uniquely written as a linear combination J equals 1 to N Bj Vj. I can write it in this way. Okay, so just take the linear transformation on U. So I have T sub U. T sub U will becomes T sub summation I equals 1 to M. Sorry, not I. U equals J equals 1 to N Bj times Vj. Because U equals, because we let the U is uniquely expressed as a linear combination of the basis vectors Vj. So because T is a linear combination, T is a linear transformation. So then I can rewrite it as summation J equals 1 to N Bj times T operates on the basis vectors. And we know it already, we know it here. So I can have summation J equals 1 to N, and that Bj times summation I equals 1 to M Aij times Wi. Same way, we can take Bj in here, into here. Then I have summation J equals 1 to N, summation I equals 1 to M Aij times Bj times Wi. Okay, now what I'm going to do is we reverse the summation approach. Do loop. We change the order of do loop, so I can have summation I equals 1 to M, summation J equals 1 to N Aij times Bj times Wi. And we take this as the coefficient, as the coordinates of Wi, the coefficients of Wi. So now we have to know that this linear combination is in W. This linear combination is in W. So here we can see that if we take Tu with respect to gamma, what can I get? It's a column vector. I start from I equals 1. So then I have summation J equals 1 to N. I equals 1 because W1. Here we want to multiply by W1. So I have A1J times Bj. Then I equals 2. Summation J equals 1 to N A2J times Bj, etc. And summation J equals 1 to N Aij times Bj. AMJ. Here I have M tuple column vector. Oh, okay, this is for the left-hand side. Okay, right now what I'm going to do is to calculate the right-hand side. So right now I'm going to calculate the right-hand side. So for the right-hand side, I'm going to calculate T is transformed to a matrix from beta to gamma times U is transformed to a column vector with respect to beta. So now we can see that because U equals to summation I equals 1, J equals 1 to N and the Bj, Vj. So what will this vector looks like? What will this vector looks like? We just take the coefficient of each vector as the column vector element. So I have B1, B2 to Bn. I have B1, B2 to Bn. Okay? And what will this matrix looks like? It will becomes A11, A12 to A1n, A21, A22 to A2n, etc. AM1, AM2 to AMN. Okay, then we just take the multiplication of T, the matrix representation of T times the column vector U with respect to the basis. Then I have A11, A12 to A1n, A21, A22 to A2n, etc. AM1 to AMN times B1, B2 to Bn. Okay, so I just take the multiplication of a matrix to a column vector. So now what can I get? I can get summation I equals 1 to n, A11 times B1, A12 times B2. So I have A1I times BI. Okay, and then I have summation, or maybe I just change the variable to J to make it consistent with this one. So J equals 1 to n, A2J times Bj, A21 times B1, A22 times B2, A2n times Bn, etc. Summation J equals 1 to n, AMJ times Bj. So we just compare the left-hand side, the result of left-hand side, and the result of right-hand side. Then we find that they are identical. Okay, so we get this result. Okay, so we have this result. So, sorry. So because for this proof stated in the textbook is very difficult to be understood, so we will just neglect it. We just follow the most intrinsic approach to get the result. So we prove that. We have already proved it. Okay, so what am I going to do is that, just as I mentioned many times, we can transform a linear transformation by using the matrix operations. Okay, so here we have T is from degree 3 polynomial to degree 2 polynomial. And there is a linear transformation defined by taking the derivative of the vectors in the degree 3 polynomial. And the beta and gamma be the standard order basis of P3 and the P2 respectively. So we have already get the matrix representation of this T as a 3×4 matrix. So if I have an arbitrary polynomial in degree 3 polynomial vector space. So for example, I can have a 2 minus 4x plus x squared plus 3x to a cubic. Then we just take the px with respect to 1x x squared x cubic. Then I can get a column vector as 2. I can get a column vector of 2 minus 4, 1, 3. I can get this column vector. So we just do the matrix operation, matrix multiplication, and I get minus 4, 2, 9. So then the resulting polynomial becomes minus 4 times 1 plus 2 times x plus 9 times x squared. So if we take the derivative here, after taking the derivative, I have minus 4 plus 2x plus 9x squared. So we have the same result. We have the same result. Okay, so here, what we are doing is we can use a simple diagram to express this operation. We can, so here, this is the, from V to W. I take the linear transformation here. But right now, we first take the U with respect to beta. Here is beta. Here is gamma. So then we convert the vectors in V into a Fn column vectors. So the basis here, for example, for the basis here is 1x squared, x cubic. But after we take the column vector representation of the vectors, the B prime becomes E1, E2, E3, E4. So we can have a U vectors, and which will be A1, A2, A3, A4, like this, a column vector. And then we do the transformation by taking the M by N matrix. This is a T from beta to gamma. This is a matrix representation of T. And then we convert it to Fm. Fm is with gamma prime. So here in gamma prime, I have E1, E2, E3. Okay, and here I have 1x x squared. So then, after matrix operation, I can have a result column vector. Then, we take the reverse approach by taking B1 times 1 plus B2 times x plus B3 times x squared. Then we get back the vectors in this W. So because the computers know how to operate this, and then after we get this column vector, that is the coefficient of the linear combination of this basis vectors. So we obtain the coefficients here. So then I can get it back here. So right now, the computer may not be able to know how to operate derivative, but we just represent the derivative as a matrix, and then we can easily do it. We can easily calculate it. Okay, so then we can get the result. Okay, so that is what this theory is going to say. Okay, and so after this, so we call this approach, we call this way as, because right now we can represent it as a matrix A. So we think this operation, we call this operation as left multiplication transformation. We call it as left multiplication transformation. So here, what we are going to do is that we strictly define the vector space in n-tupled column vectors and m-tupled column vectors. And we represent the transformation from n tuple column vectors to m tuple column vectors by a matrix A. A is an m by n matrix. And then we call this so whatever x here, we call this transformation as left multiplication transformation. We denote it as LA. And then LA x equals A matrix times x. Because right now x is an n-tupled column vector. We only define n-tuple column vectors. So in this left multiplication transformation, all the vector space are column vectors. All the vector space consists column vectors only. No polynomial, no other vectors, only column vectors. So let A be an m by n matrix with entries from a field F. And we denote by LA is the mapping from n tupled column vectors to m tupled column vectors. And we define it LA of x equals A times x. So we transform an n tupled column vector into an m tupled column vectors. And so this is a metric product of A and x. For each column vector, x belongs to n tupled column vector space. So we call it as left multiplication transformation. So if I have a matrix A, which is a 2 by 3 matrix, 1, 0, 2, 1, 1, 2, and then I have an x, which is 1, 3, minus 1. So the left multiplication transformation will become A matrix times x column vector, and then we get the resulting vector here, 2 tuple vector here. So that is the left multiplication transformation. So right now, for the left multiplication transformation, we only deal with matrix and the column vectors only. We do not care what will the original vector space look like, because we have already tagged the column vectors in V by taking its coefficient coordinate vector. Okay, coordinate vector with respect to beta. So we have already transformed the vectors in V into a column vector. Okay, so then the rest of them, we have a lot of description. And so for this linear transformation, the matrix representation, it will becomes A, and then if the LA equals LB, which means that A matrix should be equal to B, and etc. So for the theorem 2.15, actually they are identical to what we have already discussed. They are identical to what we have discussed, except for that we give a new notation, LA, this kind of linear transformation. So if we transform it to T, everything had already been proved. So I'm not going to go through the detail of this theorem 2.15 either. Okay, so the next one is let ABC be matrix such that A times BC is defined, then the associative law is valid for the matrix operation. And actually, this theorem is also redundant because it can be found here. It can be found, let me see, here, E. It can be found in E. So it's kind of redundant. So I'm not going to prove it either. Okay, so we will finish this session, composition of linear transformation and the matrix representation. And the next one will become, we will discuss the invertible, whether the operation, this linear transformation is invertible or not. And what kind of criteria are needed to have an invertible transformation. Okay, so we are going to discuss this on next Wednesday. So let's finish today's class.